Good morning, everyone. My name is Vinicius Frayze David, and I'm a researcher in the Institute of Psychology of the University of São Paulo. I am a psychologist, but I have been working with statistics for some years. And today I will talk to you a little bit about the use of mixed models to analyze twin data. I will use almost no mathematics. The idea here is to show what it can do more than how it works. Usually when I talk about statistics with other researchers, most of them identify it as its purpose, which is to teach people to use a limited sample to make intelligent and accurate conclusions about a greater population. In this sense, statistics is viewed as a tool, as a mean to an end. But statistics is also a field of knowledge in constant change, and we have to keep track of the new developments that can help us in our studies. And what are the issues with twins designs? Probably the simplest design that we can have is the one we want to compare two groups in a particular trace. This is what we have. Several subjects in group A, each one with observed trace, and another group B with its subjects and its observed traces. This is simple, and we can compare many characteristics of the distribution of the traces between groups. When you have to do that with twins, at first glance it doesn't seem very different. We still have two sets of subjects and its observed traces. The problem is that these are not independent subjects as they were in the first case. Here we have pairs, pair 1-1 and 1-2, pair 2-1 and 2-2, and so on. And as they are pairs, we could expect them to have some covariance. More than that, we are very interested in the value of this covariance. After all, if we find that, let's say, monozygotic twins have a bigger covariance than dizygotic, we can suspect there are some genetic influence on this observed trace. Here's an example. If I measure the heights of monozygotic pairs and dizygotic pairs, we can see that the monozygotic heights are much more similar between siblings than dizygotic ones. And so there's probably a genetic influence on this trace. We know there is. In this case, this is just an illustrative example. And what do I mean when I say genetic influence? Well, we know that heritability is defined as the fraction of phenotype variability that can be attributed to genetic variation. We can illustrate that with the simple formula. It's a proportion of two variances. We also know that the most used model in heritability studies is the ADCE model. It divides the factors that can influence a person's trace between 3 genetic factors and 2 environmental ones. So we have an additive, dominance, and epistasis genetic effects, and then we have common environment that are experienced by both twins, and unique environment that is experienced by each one differently, using the same formula that indicates the variation of each of these factors. We can now describe heritability as the variance of additive, dominance, and epistasis effect over the total variance of a trace. We can use submodels of ADC model too, if we exclude some of the factors. One of the most common is the ACE model, or ACE model, in which we consider all the genetic variation to be an additive effect. So we are interested in variances and covariances. How can we calculate these covariances that we are so interested in? Two of the most used techniques are the intraclass correlation coefficient and the structural equations modeling. The ICC quantified the degree to which individuals from a fixed degree of relatedness resemble each other. It's interpretable as a common Pearson correlation from -1 to +1. The biggest difference to a regular Pearson correlation is that the order of the pair is not important. What is what we need, because usually there is not a good reason to select a twin as number 1 or number 2. The structural equations modeling is the most common model, have been the most common model in twin studies for a long period. It's a very versatile model. It uses several regressions that can be calculated at the same time, and there's the possibility to use observed and latent variables at the same time. Although these are interesting approaches to use in our studies, they have some limitations. For the ICC, the most notable limitation is that it compares only two subsets, for example, monozygotic siblings or dizygotic siblings. If you have several subsets like zygosity, gender, age, etc., several analyses will be needed. For gender, you have to calculate one index for male monozygotics, other for female monozygotics, then male dizygotics, and then female dizygotics, and so on. It increases the chance of type 1 error. And of course, you will need a larger sample size to do that. For situational equation modeling, we know that most of the procedures that have been suggested involve known standards and complex model specifications that are challenging for the average user and thus susceptible to errors. Convergence problems have been observed in some procedures, so maybe it doesn't work properly for you, for your study. Some of the most promising approaches are not easily available in conventional structural equation modeling softwares. And again, we have this problem of sample sizes. When you can make a sample size calculation, but usually the rules of thumb is that you need more than 25 observations per parameter. So we get to the mixed models as an alternative. The main difference of mixed models to others, like the regular analysis of variance, is that mixed models include a random effect to our fixed effects. A random effect supposes that the data come from a hierarchy of different populations, and the differences are related to this hierarchy. It has the assumption that individual traces are not related only to independent variables. There is the presence of a non-random error. It is very used in educational studies. Let's say we want to compare results of a test from children of private or public schools. And we have data from some schools of each group. The nature of the school is our fixed factor, private or public. But we have to consider the school itself as a random factor. After all, we expect to have some covariance due to the school, and not only for its nature. Some schools will have better facilities, better teachers, and so on, despite the fact that they are public or private. And this logic have been adapted for twins designs. We have some fixed factors, but we also expect the individual traces of our subjects to be related to the trace of the other sibling. So, in twins designs, we use the pair of twins as our random factor. And now we can calculate the covariance among them and consider that in a more complex analysis. The total variance of any mixed model is the sum of the random factors and the residual variance. So here will be the variance of the pairs plus the residual variance. Which leads us to a second problem for twins designs. The first one was to deal with the pair covariances, and it's similar to many other studies. It's not much different to the school example I used before. But when we use school as a random factor, for example, we can assume some kind of regular distribution among schools. And so we can use only school as a unique random factor. But with twins, we want to calculate different and very specific covariances to investigate to which extent our traces can be considered heritable. We need to know at least two covariances, one for the monozygotics and other one for the dizygotics. These are just some examples to illustrate how the possible difference in the covariances can lead to different conclusions. It's not very important what is in the table, but just to show that it's important to know the two covariations. So what do we have to do? We need to separate dizygotic covariance from monozygotic ones. And recently there was developed a way to do that using mixed models. It can be done by separating a covariance that is function of the pair of twins, regarding the fact that they are monozygotic or dizygotic, from the extra covariance that is due to the pair that be a monozygotic pair. In other words, the difference between the covariation of monozygotic and dizygotic pairs. So now, our total variance will be the variance of the pairs plus the extra variance of monozygotic pairs plus the residual variance. And how do we do it? I'll try to show you with an example using Stata, but it can be done in R, SAS, or even SPSS using the appropriate commands. The first thing you need to do is organize your dataset. Each subject must be in a different row, and because of that, you will need a variable identifying each pair. You can use any number you want as long as it's the same for each pair, and each pair has a different number. Then you can have your variables of interest, like zygosity, gender, or any other. This is no different from any other analysis. The trick is to create these additional variables. They will be responsible to separate the monozygotic covariation from the dizygotic. You firstly will identify your subject as being monozygotic or dizygotic. The easiest way is to put zeros for dizygotic and ones for monozygotic twins. Remembering, you have to declare it for every subject, even knowing that the sibling will have the same number here. Then you create two new variables that I'm calling here DZ1 and DZ2. You have to assign each of the dizygotic twins from each pair to one column using zeros and ones. The first twin is 1 and 0, and the second is 0 and 1. It doesn't matter which one is which, as long as they are assigned differently. Monozygotics will only have zeros here, since they were already defined in the previous column. And then we have our comments. Here we have two examples that can be modified to fit different designs. You declare that you're using a mixed model, then you have your observed trace, and then the fixed factors. Here I used only male, that is my gender variable, and here there is a more complete model. The most important part is here, when you declare your two random effects. The first one is the pair random effect, independently if it is monozygotic or dizygotic. It will calculate the covariance of the pair that are common to monozygotic and dizygotic twins. The other one is only valid for monozygotic. It will calculate the difference of covariance between monozygotic and dizygotic pairs. Then you can specify the structure for the covariance matrix of the twins. Usually you can consider it to be identity. The main difference between these two commands is that on the first one it uses maximum likelihood estimation with a chi-square distribution, and the second one uses a restrictive maximum likelihood estimation with a t-distribution. As a rule of thumb, if you don't have a better information to choose between them, if your sample is small, use the restrictive. If it's large, you can use the maximum likelihood. And then we can look at the outputs. The first one is very like any other analysis. You have your estimate there, your errors, your statistics, values, p-values for each factor, and you say that it's just the same. The interesting part is this other table, where you can find the values of our variances. The first one is the part of the variance due to the covariance of the pairs. Here we can see how the pairs of siblings are close to each other regarding the zygosity. The second one is the increase of variance explained by the covariance for being monozygotic. This is only valid for monozygotic twins. And the third one is our residual covariance, the portion of the variance that is not explained by the fact that they are siblings, mono or dizygotics. Remembering the previous formula, the total variance is the variance of the pair plus the extra variance of the monozygotic plus the residual variance. Now we have some values. And what is the common variance of the pair? Well, if we are using an ACE model, what is common for every pair regarding zygosity? We have at least half of the genetic similarity and the common environment. I'm also assuming here that the twins were raised together. This is the extra monozygotic variance, the monozygotic covariance minus the dizygotic covariance. Since monozygotic are expected to have the double of the genetic similarity when compared to dizygotic, we can expect this value to be half of this effect. So it's half of the additive effect. And the residual variance is what's not explained neither by the additive effect nor the common environment, if we are using an ACE model, so we can assume it's the unique environment effect. Putting in numbers, we can conclude that 15.6% of this trace variation is due to common environment variations, 60.7% is due to additive effects, and the unique environmental variation is responsible for the 23.6% left. Now, I have to say that mixed models also have some limitations. First, show you how to perform it with NACE models. And we know that this model can overestimate the genetic effects, so we need to be careful in the sense. It is possible to include dominance and epistasis effects, but this gets much more complicated and lost the advantage of being a simple model. The way I show you, I only analyze one independent variable at a time, but you can do it with several ones. That's not that hard. You just need to include another random factor that will be the subject itself. I also use a linear model, but you can use generalized mixed models that deal with different distribution like binary, ordinal, and so on. And finally, as far as I know, if you have both observed and latent variables as independent variables, there is not a solution yet for mixed models. This is a real limitation, and thank you.